guys, today we're going to talk about acids. So first thing you want to look at is just their dissociation reaction. So an acid is defined as anything that's willing to give up a proton when it's added to another solution. So when we write an acid, if we're just writing a basic nomenclature that'll represent any acid, we're going to write HA, and then if you're looking at the dissociation reaction, you're going to add water. And of course you want to make sure this is aqueous, this is liquid because it's water, and then if it's anything but a strong acid, so any weak acid, you're going to have forward and backwards arrow because your acid will be able to donate and reaccept its protons. So then you're going to get H3O plus because water is going to pull off a proton from your acid, and that's going to leave you with your A minus anion. So that's your basic dissociation reaction. We can know a lot from this, especially when we have Ka. So Ka is going to be your dissociation constant for your particular acid, and this is always going to be another equilibrium constant, so you're going to have your products over your reactants. And again, this is in terms of concentration, so you're going to put in any terms in this equation that are not solid or liquid, because otherwise your concentration is just going to fundamentally be 1. So for this particular general equation, we have concentration of hydronium times the concentration of your A minus all over the concentration of HA. So we know that the larger Ka gets, the stronger your acid is, because that's saying that it's more willing to give up its proton. And so that means that as you increase the concentration of your hydronium and your anion, your Ka is going to increase, so your acid is going to be stronger. So where you can go from here with your Ka is you can make a rice table. So again, rice stands for reaction. Write this in red. So we have reaction, initial, change, and equilibrium. So from there, you write out your reaction again. So anything that's part of your reaction that has a concentration value. So you're going to add HA, your hydronium. Again, you don't need water because it's a liquid. And your A minus. And then you'll make 3 columns. And so if you're given a basic equation where you know the starting concentration of your acid and you want to find the ending concentration of both your acid and your products, then this is how you're going to do that. So let's say you start out knowing your HA concentration. You'll put in that concentration there. You'll assume that the starting concentrations for both your products are 0. And then you know that however much your acid concentration decreases, your product concentration has to increase. So we'll go minus X and then plus X. And then for your equilibrium, you're just going to pretend that there's a summation line here. So we have concentration of your acid minus X, and then plus X, and plus X for both your products. So where this gets important is you can plug in these values for your Ka equation. So remember how we had the concentration of our hydronium and our anion? We're going to pull those from right here and here. So you'll have, this will be equal to X times X, and then the concentration of your acid is going to be this guy right here. So you'll have HA minus X. And then we're going to make a simplifying assumption in that your change for your overall reaction, so your X is going to be so small that it won't even matter on the denominator. So to simplify this equation and make it a little bit easier to solve, we're going to come down here and say that Ka is equal to x squared over HA. So then we simply solve for x and plug that back in here, and then we can find the final concentrations of your acid, your hydronium, and your anion after you've dissociated your acid and water. So hopefully that helps.